Good morning, everyone. With immense joy and gratitude, I warmly welcome you all to day 4, the final day of the IEEE GRSS Summer School or Hardening SAR and Machine Learning for Indian Agriculture. It has been an incredible journey of learning, exploration, and innovation over the past few days, and today marks the grand of this enriching experience. Today, to deliver the session, we have Mr. Alejandro with us today. Now, it's my great privilege to introduce our esteemed guest, Dr. Alejandro C. Ferry. He is currently a professor of statistics and data science at Victoria University, New Zealand. Professor Ferry had made significant contributions to the IEEE Geoscience and Remote Sensing Society, serving as editor-in-chief of the Letters General, distinguished lecturer, vice president for publications. His research focuses on data visualization, statistical computing, stochastic modeling, and applications in signal and image processing and network. Thank you so much, sir, for joining us today. We are really honored and grateful to have you here. Now I invite Mr. Alejandro to please come onto the dais and deliver the session.
Thank you so much for the kind introduction. Thank you very much, Professor Busmi Shaurasia, for organizing this. Nice meeting you. Hello, everyone. I have material. I will set up my computer, so I have a presentation for you. But I want this to be much more a conversation than a presentation, right? Because presentations, you can pick the material. I will leave the link for you to have the material so you can go through it. I think it's much more important if we can discuss, if we can talk. But in order for that to happen, I need you to stand up and talk, right? So I expect you to participate. So just a second, I will set up my computer. More or less the whole day, right? We have the morning and the afternoon. But this talk only makes sense if you have an idea of when and how to use this technique and this family of techniques. So first of all, I need you to tell me the highlights of what you have learned in this school. Who volunteers? Who wants to talk? You stand it up. How about telling me? Yeah, why not? No, I want students to talk to. Yeah, who can tell me the highlights of what you learned during these days? Nothing? If nothing, no, why not? Tell me, what have you seen? Have you learned how to get SAR images? Yes. Where? Since you were so assertive, your name?
Hey, good morning. My name is Parthish. So we kind of got links to certain websites, and from there we downloaded SAR data and the biomass data of it, of Elvin band.
Excellent. So now tell me, intensity data, polarimetric data, polarized data, which sensor? Earth, Sentinel, which sense? Do you remember which was the
It
sense?
was NISAR.
NISA. Wonderful, wonderful data set. Another voice. Which spatial resolution? Another voice. So what's the size of the pixel? Approximate.
I think it was 5 meters.
Wow, very high resolution. Very high resolution. When I started working with SAR, we had images of 300 times 300 meters on ground. So you have 5 meters. Amazing. A different voice. I want somebody else to reply. L band, which frequency or which wavelength it is? What's the wavelength? You know what the wavelength is? The wavelength?
1275.56 frequency, I think, yeah, megahertz.
Sorry, again?
1275.56 megahertz.
Okay, and what's the
Frequency.
approximate wavelength? That's the frequency, approximate wavelength. Yes, yeah, around 20
20s, yeah.
what? Centimeters, right? So let's do a small exercise. Let's imagine a pixel here, 5 meters, you told me, right? Something like that, right? So this would be the size, approximate size of a pixel on ground as seen by NISAR, right? In which wavelength? 20 centimeters. What does it mean? The value that I get there is proportional to what? To what each element in this area returns, right? The return. But what is an element? Can NISAR see, for instance, a needle in a 5 times 5? No. What does NISAR see? Wavelength. Things of the order of the wavelength. So it will see things of the order of 20 centimeters or more. Yes, 20 centimeters or more. Smaller things like that, well, unless there are many of them, the sensor will not see them. Good. What is the school about? Agriculture, right? Differently from urban studies, different from forest studies. What are typical agricultural targets in India? Yes, more specifically, yes, but what type of vegetation are we interested when we're talking about agriculture? Crops, for instance, of rice. What's the size of a rice plant? It goes from this to this. So it will be seen by NISA. Yeah, that's why it's 20 centimeters, right? That's why, because it's sensitive to the things that we want to see. Good. So do we have a clear idea? Our sensor, NISAR, sees in the ground things of this size, and inside this area integrates the return from objects of the size of 20 centimeters. Okay, so if we have rice, how many plants of rice do we have in a 5 times 5 region? $22.40, that's very precise. Exactly, 2240. At different growth stages with different humidity patterns, right? So we have, would you say that 2240 is a few or lots? A few? If I ask you to sum numbers 2240, 2240, you mean 2,240 objects. At 20, between 20 and 40, between 20 and 40 plants or 20 and 40 pads?
In 5.5, if I am taking the 25 square foot, one complete area, so in that they will put like that 20 to 40 as per the requirement, like that growth.
Perfect. So between 22 and 40 in different growth stages. So depending if it's just born, it will be barely visible. If it's grown, it will be more visible. That is what we want to see. If we are studying rice, that is what we want to see essentially. Wonderful. So how do we see that? Now you have made the course, you have downloaded nicer images. How do you use one of those images to count the number of backscatterers? Let's not talk about plants. Backscatterers, elements able to return signal. How do you count them? In 1 pixel, from 1 pixel, you have only one value, right? Imagine an intensity image, your value is 14.73. What does it mean? Not much. It's difficult to say, to relate the value to the object, right? Because we have 14.73. In the next pixel, 17.92. It varies. How can we extract information from those varying values? How do you do that? Your first approach, what would it be? Don't worry, don't be afraid to make, there are no mistakes, to make strange proposals, because we're doing image processing. We try many things until something works. So what would you do? Your problem, I hire you and I tell you, from this region in India, in this date, this particular date, I want to know the average, attention, important word, the average number of backscatterers in this area. What do? You can go to the field and count, of course, but that's not remote sensing. How do? That's what we are trying to do with this technique, counting the number of things, right? But I will go a big circle around with a few mathematical things, a few statistical things, but at the end, what we want to do is we want to count the number of things. So let me give you a spoiler that's, hello, a spoiler that's not on the slide. What's the classical way of doing this? Well, you do a local filter. You know what a local filter is? I stand in this pixel, look at my surrounding values, do something, go to the next pixel, look at the surrounding values, take, for instance, the average or whatever. That's a local filter. What is the most basic local filter that can tell me in a SAR image if I have a few or many things. It's called the coefficient of variation. You know the coefficient of variation? It is the standard deviation divided by the mean. Why is it so important? Because in the metadata of our image, there is an information called equivalent number of looks. If I have many things, the coefficient of variation will be of the order of 1 divided by the equivalent number of looks. The higher the number of looks, the smaller the coefficient of variation. The larger the coefficient of variation, the smaller the number of looks. But how comes? If the number of looks, it's in the metadata. Are you following me? Are you following the rationale? I read the metadata and it says 4 looks. Okay, so I should expect coefficient of variations of the order of 0.25. So I measure here, measure there, 0.22, 0.27, it's okay. All of a sudden, 0.01. It's very small coefficient of variation, very small. What does it mean? A strangely flat area, almost no variation. And I go, remember, I was expecting 0.25, so I move, and then 20 or 70. Extremely high coefficient of variation. What is happening there? Extreme variation. Where do I see extreme variation? When I have a few backscatterers. So the coefficient of variation tells me roughly the number of backscatterers, provided I know the number of looks. That is, I would say, SAR image analysis version 0.0, the basics. In a SAR image, you seldom look at the mean image, at the average. You mostly look at the coefficient of variation. What I will talk about, what I will present, is an improvement with respect to the coefficient of variation. So I will speak about entropy and lots of things, but remember that what I want to do is something that performs better than the coefficient of variation at telling me how many dumb things I have in average per pixel. Right? Are we clear about that? Yes? Second point, if anything is not clear, you stop me. We have time, right? Good. Okay, so we will start. At some point it will, yes. So this is a joint work. This is part of Janet's PhD thesis. She's from Colombia. Professor Paolo Gamba is from Italy. Professor Abrão Nascimento is from Brazil. And Professor Andrea Rey is from Argentina. So a very international collaborative work. As I said, this is the last of a series of papers by Janet Alpala in her PhD thesis. So, and this one that I am presenting here is under review in transactions, in IEEE geoscience remote sensing transactions. The other two that I will mention during the presentation have already been published in IEEE geoscience remote sensing letters and in remote sensing. Okay, so this probably here. It refuses to work. Okay, I'll do it by hand. So what do we have? SAR is one of those image modalities. Okay, thank you. Thank you so much. So SAR, synthetic aperture radar, is one of those imaging modalities that uses coherent imaging. It's not the only one. I will show you something interesting. Laser pointer. All of you have played with a laser pointer, right? So I want you to tell me what you see. Do you see a flat spot? What do you see? Yeah, you see speckled pattern, right? Have you seen this before? Check it, look at this. Do you see a flat, white, or do you see speckles, bright and dark? Speckle, because laser is coherent light. That's why it's strong. Look at this. The speckles here are beautiful, beautiful speckles. That is a speckle, an interference pattern. Look at this. You see? You see the speckles, bright and dark. It's not like a spot of light. There is an interference pattern. Ah, this is beautiful here. You see? Yeah. I'm showing one by one. Look at this. You see the pattern? You see? It's an interference pattern. And now comes, hello, why don't you join the others and help me? Look at this. You see the speckle? Join another table. Look at this. You see? It's not flat. It's a pattern of bright and dark points. You see it? If you're not convinced, I can lend you my, or pick any laser pointer. You see? Very different from a spot of light, right? Because this is coherent illumination. This. Right? And the last one, I already showed. These guys were not convinced. You were not convinced. Play with it and then return. Okay, so speckle is an interference pattern. If I could hold my hand very still, it won't change. It wouldn't change. It would be totally deterministic. But any small movement of my hand makes the pattern change. So, message number one, when you write your paper for a journal, when you mention speckle for the first time, don't say speckle noise. Speckle is not noise. What happens is that it's a deterministic interference pattern, but it's so hard to model deterministically that we prefer to model it as a random process, as noise, right? So message number one, important message number one. And we have speckle with laser, ultrasound B. These images that we make for medical purposes, sonar, a very active research area, underwater imaging, and SAR. Well, when we have coherent illumination, instead of seeing a flat, bright spot, we see this pattern, and this pattern kind of makes things difficult, more complicated. This pattern arises from the interference of the incident wave and the reflected wave. To the right of the slide, at the bottom, you see 3 examples of true SAR data, so over an agricultural field. Oops. It's my finger. I always try to configure it. It will come. I always try to configure it not to go into sleep mode, but I forget how.
Connect it again.
It won't go to sleep again. So here we have 3 samples from actual SAR images: an agricultural field, a low forest, and high forest. Right? Guess what's here? Do they look like above and below? So the above looks like a very complex area where ranging from, I don't know, sand to forest, right? No, it's simulated. It was made with code simulation, because the statistical model of SAR is so freaking good that you can produce things like this. They really, really look like true data. So it's not one of those cases. Oh, that's wonderful. Thank you so much. Like this? Yes? Okay, wonderful. Thank you so much. So the statistical modeling of SAR data is so incredibly powerful that we can produce plausible things like the image above with relatively simple statistical models. Remember, we're modeling something which is deterministic, but we say, I give up, it's too difficult to model this deterministically, so I will put statistics. And it works like a charm, works wonderfully. Next slide, please. There are a few animations, so don't worry. And this is an X-ray of what happens in a single pixel. What I am modeling here is a single pixel in which there are 10 backscatterers. 5 times 5. Backscatterer is anything larger than 20 centimeters. If I see only 10, what am I looking at? Well, maybe young trees. Only 10. If were old trees, it would be only 1 or 2. If it was grass, there will be infinitely many. So this is what I might be seeing when imaging young trees with NISAR. What is that I am seeing here? Tree number 1 returns this complex signal, real part, imaginary part. All of you are aware of complex numbers, right? Good. So I am working with electromagnetic waves. I model them with a real and imaginary component. So S1 is what my first young tree returns. On top of it, S2, my second young tree returns. On top of it, S3. These contributions add up coherently, right? Some of them constructively, others destructively. A coherent sum of vectors. At the end, my sensor measures this, the red vector, in 1 pixel, right? Now I move to the next 5 times 5. Well, I may have, I don't know, 12 trees, and so on, right? At each pixel, coming back, sorry, it's my, you know how it will improve? If we plug the computer, it will stop bothering. And this is when you start thinking about interesting questions to impress your teachers. Sorry for the mess, but probably this will keep the computer from stopping. Yeah, sure. Sure. Move. Yes. Okay. Next, please. The red vector is a sum of m elementary scatterers, m, 10 in our plot. Each scatterer returns a complex quantity, SL. I will give you the link to this, right? You can download these slides. You can do better than that. You can compile these slides. So each elementary backscatterer, each tree, returns an amplitude and a phase, complex numbers, an amplitude and a phase. And I can decompose this sum of m complex numbers into a sum of m real numbers, real values, plus a sum of n values that will be the imaginary part. So I decompose my return S into a real part and an imaginary part. Now I want to model this statistically. Yes, if I knew the distribution of the amplitude of the return. And if I knew the distribution of the phase of the return, then problem solved. But I don't. I usually don't. So what we do, now tell me, you have all taken course in statistics, right? What do statisticians do when we don't know what else to do? Which theorem do we use? We try to use the central limit theorem. Why? Because it's wonderfully powerful at describing what? Some things, right? The central limit theorem tells me that when I sum and I scale conveniently many things, the sum will be normally distributed, right? Okay, so we state here the conditions for which, under which we will have a central limit theorem for this quantity and this quantity. Which are the conditions? First, M is infinitely large. Remember, central limit theorem, infinitely many terms. Okay, so we need infinitely many objects. Do we always have that? No. And we will discover that. That's what we will do. We will discover when this does not hold. So, our observation S is the sum of M object if we have infinitely many scatterers and the amplitudes are independent. Now, I need you to exercise your imagination. The amplitudes describe the height or the biomass of the trees. That is what A is, essentially the biomass. Independent trees, do I have any reason to suspect that their biomasses are talking to each other? No, they should be independent, right? So the second bullet, the amplitudes are independent, is okay. But notice that I added something else. The maximum variance is limited, so I am not mixing a sequoia with young trees. I'm mixing in the pixel comparable things. There's none of them is huge compared to the others. The third bullet, I say that the phases are independent and they don't bring any information. They are uniformly distributed. And everyone is independent. Amplitudes and phases are collectively independent. Under those conditions, being the first, the one that we are focusing, under those conditions, the real part and the imaginary part behave in such a way that I can describe them with the central limit theorem. So they are normally distributed with zero mean. Am I doing that? Under those conditions, the real and imaginary part are asymptotically zero mean, normal, identically distributed, and independent. Zero mean, normal, identically distributed, and independent. Okay, just don't freeze there. No, it's okay, it's okay. Next. Does this central limit theorem work in practice? Because we statisticians, we use it all the time, but we often fail to check if it works. Does it work? Look at this image. This image is from a region in Italy. The resolution is of the order of 10 meters, 10 times 10 meters. It's in L band, 20 centimeters. All these are agricultural parcels, right? All these are agricultural parcels. This is an urban spot. We will talk about that in a minute. But the rest is agricultural. So 10 times 10, 20 centimeters, we should be observing the central limit theorem. Next, please. And I picked a sample of over 15,000 observations, values. And I picked the real part. And this is the histogram. On top of the histogram is zero mean normal density. The fit is just stunning. It's very difficult in practice to see statistics work so well. It's amazing. But we seldom work with the real part and the imaginary part. What we often do is we move into the intensity format, right? In intensity format, if we have normal, in intensity format, we will have exponential. Look at that histogram with the fitted exponential density. It's amazing. It looks like cheated, but it's not. It's true, I promise. I didn't use ChatGPT either. This was done by hand by myself, right? So it's stunning. The agreement between theory and practice in SAR statistics is stunning. This is what brought me into this field. Next, please. But what happens? The exponential distribution that we have with intensity under the normal, under the central limit theorem is very noisy. The noise is very high. So what do? We usually take averages. And how many averages? L. How do we call L? Number of looks. So the number of looks is the number of independent averages that I took to reduce the noise. Good? Gamma follows from the average of exponentials. Good? Okay. So if I started with exponentials, the average should be gamma. Which gamma? This parametrization. Well, this is a particular parametrization. This is the probability distribution function, the probability density function of SAR image following a gamma distribution parameterized by the mean and by the number of looks. This might look a bit different from what you have seen in theory, but it's just a different parameterization. It's very convenient. Now it's a checkpoint, and I need you to answer. If I pick an image and I fit the gamma model, and the gamma model is good, do I have any reason to believe that I have only a few backscatterers? Or fitting a gamma model tells me most likely you have infinitely many backscatterers. Question again. I have my image. It's multi-look. I fit the gamma model. Very good agreement. Do I have any reason to suspect that I am looking at buildings? Or most likely I am looking at grass or crops? No reason, right? Why? Because, and look at this, this is the connection between data, statistics, and what happens in the ground. My theory says that if I have infinitely many backscatterers, M, then I will have normal, normal. Then the sum of the squares will be exponential. Then sums of exponentials will be gamma, right? If I have gamma, because I checked, I made a histogram and it works, I have no reason to suspect that anything went wrong, right? But if I don't have gamma, what might be happening? M is probably small. M, the number of backscatterers, is the number of objects around. So if M is small, then the gamma won't fit. Is that bad? Do I cry? No, it's information. It's telling me that I have other things. And if I am able to count M, then I have understood my image, right? Are we good? Are we clear where we're standing? If not, please let me know, because now I am going to put math on top of this and recover the information. Are we good? Yes? No? No? Not good? Any feedback, please? We have time. I came from New Zealand. Use me. Oh, okay. I will trust the ones who agree. Okay, so if we fit a gamma model with a number of looks that's in agreement with what we read in the meta file, probably I am looking at grass, bare soil, sand, things that are infinitely many things in my pixel. Next, please. What happens here? This is a beautiful image from Dublin. Well, we have sea, we have the sea, and we have a few parks. These are parks, but the rest is mostly urban. 10 times 10 round. How many buildings do I see in a 10 times 10 meter? One at most. So will M be infinite? No. Will I have a gamma distribution? No. What will I have? Well, when M is finite, the number of backscatterers, it happens in forested regions, urban areas, then I can say that the backscatter fluctuates among pixels, and we say that the speckle is not fully developed. That is a technical term. Fully developed speckle is the previous one, M infinite, right? M infinite normal exponential gamma. That is fully developed speckle. When anything fails and the central limit theorem does not hold, I don't have fully developed speckle. Next, please. How can we model non-fully developed speckle? Well, for you to have an idea, the fully developed speckled model was proposed in the 50s by Goodman in the context of optical statistics. By the end of the 70s, Kong and others proposed the K model to describe non-fully developed speckle, and they obtained the K distribution, which is numerically and mathematically cumbersome. And this distribution was part of my PhD thesis. We're talking 1993. This is also for non-fully developed speckle, but mathematically more tractable than the K distribution. And in the 20s, in the 21st century, there was an explosion of models for non-fully developed speckle, but still this is considered the universal model. So it's good to take a look at this, because this model is very, very flexible. And look at this. This model has 3 parameters. The name of the model is G0, SAR for SAR. It has 3 parameters: mu, the mean, easy, right? The mean. L, the number of looks. Alpha is the naughty thing, is the sexy thing here. Alpha by construction is negative. Forget about negative. Think of the absolute value of alpha. The absolute value of alpha is proportional to M, to the number of backscatterers. So if I can estimate alpha, I know the number of backscatterers in the ground. Gorgeous. Well, that's why it deserved a PhD thesis. The paper has around 1,000 citations. It's widely known and used as the universal model. It's not as bad as it looks. You have taken a course in statistics, right? If I show you a probability density function you must not be afraid by all the things in the equation. You must look at what we call the kernel, the essence, the heart of the distribution. Where is the heart of this distribution? The heart is here. This is a constant. This is the heart. And what do we have here? Z to the number of looks minus 1, easy, couldn't be easier, divided by a constant plus number of looks times L to a power. Extremely simple. It looks weird, but it's extremely simple. Have you heard about the F test? This is the Fisher probability density function. This is the probability density function that we use in the F test in a totally different context and a totally different parameterization. But this is the Fisher-Snedeker distribution, right? So this is what we use to model non-fully developed speckle. Fundamental question that you must ask whenever a crazy dude like me tells you this. What am I telling you? If we have fully developed speckle, use the gamma. If we don't have fully developed speckle, use this. Useless, because you don't know. There's no gnome, there is no creature that tells you, I am fully developed speckle. No, you have data. So what do you use? That's the importance of a good model, because you don't need to use the gamma or the G0. This model embeds the gamma as a particular case. So if you use only this model, you will be using everything, right? That's the beauty of this model. When alpha goes to minus infinite, this model becomes the gamma. What is alpha goes to minus infinite? The absolute value of alpha is, I told you that, m, proportional to m. So if minus alpha goes to minus infinite, so if minus alpha goes to infinite, the number of backscatterers goes to infinite, and if it goes to infinite, we have what? The gamma, and it works, right? So that is one of the things that I proved in my thesis and in the paper, in the original paper, that this thing converges to a gamma distribution. It's not trivial, but it's beautiful. Okay, so we have one big model, this one, that has the gamma as a particular case. And this model is able to measure the number of backscatterers. Next, please. Okay, so we have two models, or if you prefer one model, the gamma SAR for fully developed speckle, the G0, which is more general and includes the fully developed speckle. We want to measure how close or far we are from the fully developed speckle situation. That's because you may think, well, why not measuring the other way around? Well, the other way around has infinitely many possibilities. Whereas fully developed speckle is a point in the parameter space. Okay, we want to do that with samples, not theory, samples. So I want to collect samples and say, this is most likely from pasture. Or most likely this is not pasture, something is happening here with samples. But not many samples, because my agricultural parcels may not be that long. Imagine family parcels. There won't be so many pixels to make the study. Moreover, I don't want a specialist picking pixels, selecting pixels. I want to make a gross, a rough selection. If I make a rough selection, there may be contamination. They enter a building in my collection of pixels. So I want to work with small samples and with the possibility of contamination. It's a nightmare. It's a nightmare. If you ask a statistician to produce a model and produce estimation that works well with few samples and with contamination, probably the person will resign. I don't. I'm stubborn as a mule. So we did this. We did this, and I will show you how we did it. Next, please. How do we do it? Look at that beautiful chart. We do it with a concept that's in the title of my talk. The concept is entropy. And the chart tells you why we don't teach entropy to our kids. Entropy is like the universal answer to who made this mess. Entropy. If there's mess, there's entropy. Or if you prefer, entropy is a measure of mess. That's a beautiful paper. The paper by Savitsky. It's in a really accessible journal. Everything is on the slides. And this guy discusses the history of the concept of entropy. Entropy is a number. It's a number that I attach to a system, and this number measures the disorder of the system. For instance, there is somebody, imagine there is somebody outside, and this person outside hasn't seen any of us. And this person wants to forecast the age of those who leave this room. It's really easy, right? Because the distribution of the age is fairly around, what, 25? Of course, I am an outlier, but mostly are around 25. So the entropy of the age is very low. It's easy to predict. But if this person wants to predict the length of the hair of the people in this room, there's me in one extreme, there's ladies in the other extreme, so it's complicated, right? So the entropy of the length of the hair is higher. The entropy describes our inability, our impossibility to predict. Look, that is entropy, and it has appeared in everywhere you can imagine: linguistics, biology, cosmology, whatever you want. There's entropy because it's a very, very useful measure. And well, those are some of the thoughts from that paper. Life is an ontology of destruction. Everything goes to a soup of no information. Everyone you love will die. The entire universe follows a dismal trek towards a dull state of ultimate turmoil. Entropy is always on the rise. So the chaos, the unpredictability is always increasing. Entropy, for us, in this paper, is a measure of disorderliness, measure of variability. The more variable, the higher the entropy. Next. So there are several ways of measuring entropy. I'm stating three. These three are three papers that I have authored, but we will focus on the last. The first version of entropy is the Shannon entropy. I'm sure you have seen it. Probably you have seen it in the form minus the sum of P log P, right? Because that's the discrete version. I am using the continuous version. The Shannon entropy is that quantity minus the integral of the logarithm times the density. The Rényi entropy is second expression, just an expression. Let me tell you that the Rényi entropy converges to the Shannon entropy when the new parameter lambda goes to 1. And the third entropy, the Salis entropy, is the third expression. And I will stop for a moment to speak about Salis. Konstantinos Salis, Greek, born, raised in Argentina, and lives in Brazil. He has been considered for the Nobel Prize in Physics several times because of this. Because this thing, the Sallis entropy, is extremely powerful at describing black holes, or what happens at the surface of a black hole. Go figure. But I use it, not yet, I use it in a totally different context. Let's look at this. Oh, back, don't spoil, back. Yes. What is the Sallis entropy? Essentially is the integral of the probability density function raised to the power lambda. Lambda is called the entropic parameter. If lambda goes to 1, this quantity converges to the Shannon entropy again. But you see, it's not complicated, right? It's relatively simple. If you know how to integrate, you can do it. And yes, you can do it. And it's extremely powerful. Okay, what do we do with this? Next, please. Remember, and now is step by step, so I need you to follow, right? Now is when you drop your cell phones and pretend that you are following my talk. We want to estimate the Sallis entropy of a certain distribution. The Sallis entropy of a distribution is this quantity, 1 over 1 minus lambda times 1 minus the integral of f to the lambda. If I want to work with this expression, I need the density, right? I need the probability density function, and I don't have it. And you know, this is the life of a statistician. We do beautiful things, and at the end we say, well, look at this is gorgeous, but I don't have it, I don't know it. So what do we do as a statistician? We estimate whatever we don't know. I could estimate the probability density function, but in SAR data, remember what I wanted to do? I wanted to work with small samples. If I want to estimate the probability density function, I need lots of samples. A few samples don't help. So what do? Okay, I make a transformation, and this is a beautiful exercise. Professor Musmi, if you want to apply this to a test, it's a good question. Transform this integral into this integral. It's relatively easy when you know how to do it. What is Q? Q is the quantile function. What is Q prime? The derivative of the quantile function. So I transformed f to the lambda into Q prime to the 1 minus lambda. Okay, that's an exercise, but why do I do this? Because this smart transformation, which is not mine, we adapted it, allows me to do the following. Q is the quantile function. How do I estimate the quantile function? With the quantiles, the sorted statistics. But I don't want the quantile function, I want the derivative. As engineers, if I ask you, how to estimate derivatives? Differences, right? What is the derivative? It's this point minus this point. Okay, derivatives. Instead of quantile function, Q, order statistics. Instead of Q prime, the difference between order statistics. So I estimate this with this expression, with this. And that is amazing. This is amazing. This is why this is worth a PhD thesis that has been praised and published. We estimate the Sallis entropy of parameter lambda with a sample Z as blah, 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 the sum of differences of order statistics. Do you know what order statistics are, right? You pick a sample and you sort it from smaller to larger. So then you pick differences. That's it, and that's it. Beautiful estimator. Okay, you see two new things, CI and K. CI is a constant, don't worry about it, and K is the spacing. So how many samples do I skip in my differences? That's K. If I choose CA like this and K like this estimator is, next slide, this estimator is asymptotically consistent and normal, so it works well. So I am estimating the Salis entropy with that expression. Do you see, and this is critical, I am saying that I am estimating the Salis entropy of the model D. Do you see the model D here somewhere? Do you see a density? Do you see a probability? Do you see a cumulative distribution function? No, it is non-parametric. It is totally non-parametric. I do not need to assume anything about the model. I just need the data. So this expression estimates the Salis entropy regardless the model. It converges to the Shannon entropy. It only requires sorting small sample. Small what? Well, 25 samples. You sort them. Then you pick differences. Very, very simple. It's not, doesn't suffer from numerical instabilities, and it is asymptotically consistent and normal. Wonderful result. Next, please. We'll put this to work, right? Okay, we will put this to work. How do we make it work? Okay, we have an estimator of the Salis entropy. What was our problem? I know you're tired, but few more slides and we will see images, right? So bear with me. What was our problem? We wanted to check if if we had infinitely many backscatterers or only a few. So we put this, we have an estimator. So we put this in the context of test statistics. And I won't go into all the details. This is a PhD thesis, but we have the null hypothesis. The sample is compatible with the gamma model, infinitely many backscatterers. The alternative, the sample is compatible with the G0 model, less backscatterers. This is called nested distribution problem. You should study it in an advanced statistic course. You can use likelihood ratio test, Wald tests, many things. But still, we want a test that performs well with relatively small samples, a test that performs well when there are outliers, and that's computationally efficient. So that's what we want to do. And what do? We based our test on an observation. The Salis entropy of the SAR model is smaller than the Salis entropy of the G0 model. That's simple observation. Next, please. Leads me to a test statistic. The Salis entropy under the gamma SAR, infinitely many backscatterers, is smaller than the Salis entropy under the G0, a few backscatterers. So I use this difference. This expression depends only on mu once I know the number of looks. The number of looks is in the metadata, and this expression depends on mu and on alpha. So what I want to do is I want to compare. I want to know where, if I am close to the right, to the left, or I am close to the right. But we don't want to estimate alpha. Why? Next. The three main estimation techniques are moments, maximum likelihood, and log cumulants. Moments often don't have solutions. Next. Likelihood becomes flat, and I cannot optimize it. Next. Log cumulants are sensitive to small outliers. So the three main techniques are not good for my problem. What do? Next. Okay. We estimate with our non-parametric estimator, and subtract a function of the mean. If we are under the null hypothesis, this quantity is practically zero. If not, it will be large. Practically zero, what does it mean, practically zero? Well, we know, remember that I mentioned that this estimator is asymptotically normal, so I can use that information to say, to give meaning to this approximately zero. And what do? We will build maps of p-values, right? This is what we will do. In practice, and what is the contribution, and what is that you must implement if you want to use this? Well, you can just download our work that has all the code, but what you should implement is the following. First of all, next please, we improved it with a technique that is not new, published 1999 by Park and other authors, that says, if you want to estimate something in a SAR image, pick a large window. Estimate. Is this estimator good? If it is, use it. If it's not, reduce the sample. Is this good? If it's good, use it. Otherwise, reduce the sample, reduce the sample. It's an adaptive window approach. The big question is, how do we know if the estimator is good? Well, read the paper. It tells you how to do it. So we use a windows of size 11 times 11, 9 times 9, 7 times 7, and 5 times 5 in an adaptive way. Next. Remember that we have lambda, the parameter of the Sally's entropy. Well, we found the optimal lambda for our problem. Our problem is detecting departures from the fully developed speckle. And our optimal lambda is 0.85 based on the bias and mean square error. Next. And we optimize the estimator by bootstrap. Have you heard about bootstrap? Yes, no? Where am I? Yes? Okay, if you heard about bootstrap, you know that it's an extremely powerful technique for improving estimators. If you want, in the second part of our talk, we can go into bootstrap. We can talk about bootstrap because that's something that you should really, really know. Next. So finally, images. Now is when you wake up. Okay, next. San Francisco, of course. Of course, we use the San Francisco image. To the left, the intensity image. To the right, the p-values of the test. How do we interpret p-value? If the p-value is very small, I reject the null hypothesis. What is the null hypothesis? Infinitely many backscatterers, textureless areas, pasture, small vegetation, sand. Low p-values are coded, look at the color code to the left, low p-values are coded between red and, let's say, greenish or reddish. All reddish colors correspond to sites where the null hypothesis can be rejected at once. Bear something in mind, that the p-value is related to alpha, which is related to the number of backscatterers. So the reddish the color, the fewer the backscatterers. So this is a map of, for instance, the number of, for instance, the number of backscatterers. How many backscatterers do we have on the sea? Infinitely many. How many, and do you see that there are differences in urban density? And I am measuring it. We can measure the density with this technique. Next, please. This is Munich image. You see the lake, the Ammersee Lake. Look at the urban spot, at the main urban spot. And look how the technique tells me that this is very dense urban, and this is also urban, but not as dense as the previous one. Because the p-value is related to the number of backscatterers through the parameter alpha. But I didn't estimate alpha. We didn't estimate alpha. We jumped into a test statistic. Next, please. Dublin. I don't know if you see it at the back of the room, but the technique identifies clearly boats or ships, clearly, because how many ships fit into a single pixel? Yeah, this one. So I will reject the null hypothesis. And it also delineates quite well park, this stadium, park, water, of course. Next, please. Foggia, the image I showed at the beginning. You see how many agricultural parcels are there. Lots of agricultural parcels. And a relatively dense urban area with a cute park here in the middle that I don't see in my SAR image. I don't see it in my SAR image, but I see it when I analyze the fully developed speckle hypothesis. Next, please. And finally, the discussion. What have we done? We formulated a very simple but powerful statistical model for what we see in a SAR image. If there is sand, I will see gamma observations in a nutshell. If I have urban areas, I will have another distribution, probably the G naught. Okay, so we detect deviations from the fully developed speckle, from the gamma model, estimating the Salis entropy. It's very, very sensitive. We improve the test with bootstrap, with adaptive windows, and by selecting the optimal value of lambda. Sorry, machine learning, sorry, artificial intelligence. We don't need training. We don't need, did you see me using training samples? No, I used what? This mathematical statistical modeling, this, I implemented and it worked, right? It's robust for small samples, effective at delineating heterogeneous regions from homogeneous ones. The results are interpretable. I can say I have a few, I have too many, or I have many. And probably the most beautiful thing, if you need entropy in your problem, but my problem needs the von Mises distribution. Use the estimator. No, my problem uses the Cauchy distribution. Use the estimator. Because the estimator does not rely on the distribution. It will measure by itself the Salis entropy. And you can make distribution-free tests whenever entropy is a good descriptor of the problem. Next, please. So these are the references, and that's it. Here's where I conclude my talk. Thank you very much.
Thank you, sir. Thank you so much for the insightful session.
Just a caveat, in the afternoon, we will discuss how I made these slides and where you can download the material from. We will see a bit about Quarto and good scientific practices. Questions? I hope I will be able to answer them. The worst question is the silence. Yes. So a simple question, is this fast enough? Yeah, pretty fast. Pretty fast. So do I need an NVIDIA whatever monster for this? No, I run all this in my computer. Right. Any other question? I have asked myself questions. Any other question? Does it generalize for polarimetric data? Yes, but I don't know how. If you want to do a PhD thesis about that. Yes, please.
Is this approach?
Yes, I will show you. I will go back. As far more. When we define more, back. Yeah, this. Okay, this one. This estimator estimates the Salis entropy. What do we have here? Give me a sample. So get your computer, open R or Python, and produce a sample of size 121 observations, right? Now sort them. Once you sort them, they are the Zs. Z1, Z2. Z1 is the smallest, Z2 is the second smallest, and so on. Define K, for instance, 3. What is the first term? Z4 minus Z1. What is the second term in the sum? Z5 minus Z2. What is, right, you see the differences. So you have all the ingredients, right? You have K and you have C. Did I ask you what's the distribution with which you produce the sample? No, I don't need that information. It's totally generalizable. If you produce it with the T distribution, with the, I don't know, the K distribution, the G0 distribution, the exponential, it doesn't matter, it works. It will give you an estimate of the Salis entropy. And now you may say, but I don't like the Salis entropy. I don't like this Constantino Salis guy. Very nice, by the way. I want to use the Reni entropy. Okay, check my paper from last year when we do the same, but for the Salis, from the Reni entropy. No, I don't like the parameter lambda. I want to use the Shannon entropy that doesn't have, okay, check my 2023 paper where we do this for the Shannon entropy, right? So, totally generalizable. Anything else? I will be around the whole day. We will in the afternoon, right, Professor Musmi? Okay. Okay.
Uh, we'll have a break for 20-25 minutes and for the breakfast, high tea, and thereafter we'll be back with the session.
And the session will be open and discussion. I don't have anything to present, right, except myself. So make use of it, right? See you soon. See you later.
Thank you, sir. Have the tea break now.